In this lecture, we are going to continue the study of vector bundles and morphisms of vector bundles. In particular, we are going to study exact sequences of vector bundles, one of the tools that takes profit of the linear structure naturally associated to vector bundles. We are going to consider some useful constructions associated to vector bundles. First, we are going to define subbundles and exact sequences. So let us begin with subbundles. Let psi be a vector bundle of dimension n, and we say that psi dot is a subbundle of psi of dimension k if the base of these two vector bundles is the same, and the total space of the subbundle f is just a disjoint union of vector spaces fx, where every fx is a subspace of ex, the fiber of the vector bundle psi at the point x. It is a subspace of dimension k for every x in M. Of course, this just defines a family of subspaces of the fibers. In order for this family to define a bundle, a vector bundle, we need an extra property, of course. And so what we need is that for every x in M, there exists a bundle chart such that the image, okay, of the points that belong to the preimage by P of U and are at that R in F, the image of such a set is U times RK times 0. What this is saying is that we are going to have a vector bundle chart over U such that every subspace Fx is actually sent by this vector bundle chart to the subspace Rk times 0 of Rn. So in these local coordinates for our vector bundle, the subspace F is given by the annulation of the last n minus k coordinates. Okay, the previous vector bundle charts provide a vector bundle atlas for psi dot. Indeed, we just need to forget this part and we have automatically a vector bundle chart in which the image of the preimage of U is just U times RK. Okay? The concept of subbundle is the analog of the concept of submanifold for vector bundles. We have submanifold, and then subbundle and bundle and vector bundle. Let us actually consider an example. Let X be a submanifold of M. We can consider the tangent space of M, okay, indeed we can write this down like this, B tangent space of M, M, and then we can consider the restriction of this vector bundle psi to X. This is also a vector bundle because X is a submanifold, and indeed this is the tangent space of M at X, right? At every point of X, we are considering as a fiber the tangent space to the whole manifold M. But we have also a vector bundle naturally associated to X, which is just the tangent space of X. And this is as a bundle of psi, of course, because the tangent space of X at a point Y is obviously contained in the tangent space of M at Y, right? So in this way, we obtain that the tangent space of X is a subbundle of the restriction of the tangent space of M to X. Okay, consider now E0 a subbundle of E. Then the inclusion is a monomorphism of vector bundles. Indeed, it is a monomorphism over the identity map. And conversely, if we consider the image of a monomorphism, okay, over the identity map, we are going to obtain a subbundle of the vector bundle E1. Another way of obtaining a subbundle is considering the kernel of an epimorphism between vector bundles. The kernel is going to be a subbundle of E0. Okay, we are going to see, we are going to study that kernel, right? So, okay, we have the kernel. We're going to call this F, and we're going to consider the kernel of Fx. What happens is that the dimension of this kernel plus the dimension of the image of Fx, but the image of Fx is the whole fiber for the vector bundle E1, okay? Because here is again over the identity, right? The image of Fx is E sub 1x. So we have this dimension, and the sum of these dimensions is actually the dimension of E sub 0x. So what we get is that the dimension of the kernel does not depend on x, okay? Because this dimension does not depend on x for the vector bundle E1, and this one does not depend on x for E0. And of course, this proves that the family of kernels is a family of subspaces of the fibers that have all these subspaces the same dimension. Okay, to prove that it is actually a subbundle is a little bit more than that, but it's not that difficult, and I'm going to lead you that task as an exercise, okay? Let us define exact sequences. So an exact sequence of vector bundle morphisms is a sequence of morphisms of vector bundles over all the vector bundles are over M, and they cover the identity map, such that for every X, we have here morphisms, linear morphisms between the fibers, and what we get is that the kernel of this morphism at X is the image of the previous one also at X, okay? So we get this condition in which the kernel is, this kernel over here is actually a subspace of psi I plus 1x, and also the image of Fix is also subspace of the same vector space on the same fiber. And what we are requiring is that for every x and every I, these two subspaces are the same one, they coincide. Okay, we can also define short exact sequences. A short exact sequence is a sequence of vector bundle morphisms covering the identity map. This is important over here, such that the sequence has this form. What does this mean? It means that the image at every fiber of this map, which is just the trivial vector space has to be the kernel at every fiber of this map. So in particular, that implies that F is a monomorphism. So that this part of the sequence is exact is equivalent to F being a monomorphism. The exactness, in this part of the sequence means that the kernel of this map, which is the whole fiber, because we are talking about the zero map, has to be the image of G. So in particular, the exactness at this part is equivalent to G being an epimorphism. And then we have an extra condition, which is that at every fiber, the kernel of G is equal to the image of F, right? If we have an exact sequence like this one, or in other words, if G is an epimorphism, we can construct a short exact sequence. Okay, what we do is just considering the kernel of this map at every one of the fibers, right? The kernel of an epimorphism defines a subbundle. Here, capital G and small g are the same, okay? And this sequence is exact, of course, because this map I over here is indeed an inclusion, so it is a monomorphism, and by construction, at every fiber, the kernel of G is the image of I of the kernel of G, because the image by inclusion is going to be kernel of G. So it's clear that it is a short exact sequence. Now we can consider an exact sequence of this type, or in other words, F is a monomorphism. And how do we build a short exact sequence, a natural short exact sequence? What we are going to consider is a vector bundle theta such that the fiber of theta at x is the quotient of the fiber of eta at x and the image by fx of the fiber of psi, right? Of course, this space, the image of psi x is a subspace of eta x, so that quotient can be considered at any point. Of course, we have to work a little bit more in order to show that theta defines a vector bundle, but again, I am going to let you that task as an exercise. So in this way, we get theta, which is called the quotient bundle of the monomorphism F. And again, this is a short exact sequence. What do we need to check out? Okay, we need to check out that this map over here is an epimorphism, but that's obvious because the quotient map from eta x to the quotient of eta x by the image of psi of x is obviously surjective for every x. So what remains to prove actually is that the kernel of this map, which is going to be the image by fx of psi x, is actually the image of this map, and that's obvious. So in this way, we can associate to a monomorphism a short exact sequence. Okay, let us consider now a new construction, which is the direct sum of vector bundles. Let us consider two vector bundles, psi1 and psi2, vector bundles over M of dimensions n1 and n2. And the direct sum of these two vector bundles is the natural vector bundle psi such that the fiber over the point x in M, over a point x in M, is just the direct sum of the fibers over x for the two vector bundles psi1 and psi2. Okay, as usual, this defines a family of vector spaces that have all of them the same dimension. We need to show a little bit more in order to see that it is a vector bundle. But in our case, that's pretty easy because we can consider two vector bundle charts for psi1 and psi2 defined in the same open set U of M, right? And there, what we have, in order to define a vector bundle chart alpha U for the direct sum of these two vector bundles, is defining alpha X, which is going to be an isomorphism between the direct sum of E1x and E2x, okay, and R n1 plus n2. And this isomorphism is the narrow one. You associate to a vector UB, where U belongs to E sub 1x and B belongs to E sub 2x, you associate this vector over here. Okay, the image by phi x of U, which is a vector in R and 1, and the image by psi x of B, the image of B by psi x, which is a vector in R and 2. And since, for instance, since in the case in which our manifold, our vector bundle is CR, these maps over here are CR, and indeed this defines in a narrow way a vector bundle chart, and it is, and we can actually show that when our vector bundle is CR, the coordinate changes associated to these vector bundle charts are also CR. If we have two vector bundles, psi1 and psi2, we consider their direct sum, and then these two maps, the inclusion, okay, that it is in every fiber a map from the fiber of the point X for psi1 to this direct sum of the fibers at the point X of psi1 and psi2 that just sends U to U0, right? And okay, pi 2 is just the projection in the second component. And this sequence is clearly a short exact sequence. In every fiber, this map is surjective. This map over here is clearly injective. And obviously, the set of vectors such that the projection into the second component is the zero vector, is the set of vectors of this form, which is just the image by the inclusion. So we have that a direct sum has associated in a natural way a short exact sequence. Indeed, two short exact sequence, because we could put psi2 over here and psi1 over here. Okay. Indeed, there exists a map, which is a monomorphism from psi2 to the direct sum, which in every fiber is just defined by this formula. The image of a vector u in psi2x is going to be just 0u. And obviously, if we consider the image of a vector u, this is going to be the projection and into the second component of 0u, which is just equal to u. So this composition of h and p2 is the of h and pi2 is the identity of psi2. Okay. Now we can use the previous example as a motivation to define split sequences, split exact sequences. Okay. So first of all, let us consider a short exact sequence. Okay, and we say that the sequence splits if there exists a monomorphism from zeta to eta, such that the composition of H and G is the identity of this vector bundle theta. It's the map H is a map over here, right? This is the definition of split sequence. This is equivalent. I'm not going to do the details. I'm going to let you that task as an exercise. This is equivalent to the existence of an epimorphism K B such that the composition of F and K is equal to the identity of psi, okay? So any of these two conditions are equivalent. And what we get when we have a split sequence, and that's the reason because it is called a split, is that eta is going to be isomorphic to the direct sum of psi. Indeed, to be more precise, it should be here the image of psi and the image of theta by h, okay? And why is that? Okay, let's consider. So we have our short exact sequence. Okay, here we have F, here we have G, right? And what we want to see is that eta is isomorphic to, oh, sorry. What we want to see is that eta is isomorphic to the direct sum of the image of psi by F and the image of theta by H, okay? And H, okay, we have it, it's a map there such that the composition of H and G is the identity map. Okay, so now consider a vector in the fiber of the point X for eta, right? And we are going to define another vector B prime, which is going to be just the image of by the composition of G and H of B. Okay, this makes sense. The image of B by G is an element of theta x, so we can apply H and we obtain again an element of eta x. Okay, so this vector over here belongs to eta x. And what happens is that we can calculate, in this case, the value of B prime by G, right? And this is going to be the image by the composition of H and G of G of B. But the composition of H and G is the identities, so this is G of B. So what we get in this way is that B minus B prime is actually in the kernel of G. Now, since this sequence is exact, we get that there exists a vector u in psi of x such that the difference between B and B prime is actually equal to the image of u. And there we have that B belongs to B prime, actually B prime belongs to the image of H. So B belongs to the sum of the image of H plus the image of F, right? So in this way, we get that actually the sum of these two subbundles is indeed eta. And we can see that actually this sum is direct. For instance, if we have a vector B that belongs to the image of psi x and the image of h, okay, what we get is that there exists a vector w in this theta x such that b is equal to h of w, right? Okay, but what we have is that since v is in the image of f, necessarily, since this sequence is exact, b is in the kernel of y. Okay, so we have this, so we get that the composition of h and g applied to w is 0, but the composition of h and g is the identity, so that implies that w is 0, and since v is the image of w, then b is 0. So any vector in the intersection is necessarily the 0 vector, and because of that property, this sum of these two subbundles is a direct sum, right? Very good. In this case, we obtain that eta is isomorphic, okay, to this direct sum, and as a consequence, since H is a monomorphism, we get that eta is isomorphic to the direct sum of psi and zeta, right? So when a short exact sequence splits, essentially we are in the situation in which the central term of the short exact sequence is the direct sum of these two vector bundles, right? Now let us consider an example. So let psi be a vector bundle, and we're going to consider the restriction of the tangent vector bundle of E to M, right? And we are going to identify M with the zero section of the vector bundle psi. So we have three vector bundles over M. One of them is this tangent vector bundle of E restricted to M, then E, and obviously the tangent space of M, right? What we have is that the projection associated to the vector bundle is a differentiable map. We're considering here a differentiable vector bundle. And so we can consider its differential. The differential of P is a differentiable map. Let's assume that everything is infinity between the tangent space of E and the tangent space of M, okay? But now we can restrict this differential of P to this space, which is a subset of the total tangent space. Okay, so in this way, we get the restriction of the differential, okay, to the tangent space of E at the points of M, which is just a map between the tangent space of E at M and the tangent space of M, right? And this is indeed a morphism of vector bundles. Okay, so Consider now this map over here. This map, it is clearly surjective, in particular because M is contained in E, and the restriction of P to M is the identity. So it is fairly easy to see that as a consequence, the differential of P is surjective at every point x of M. Okay. Well, we can consider here the tangent, the vector bundle E. How we do this? We have here this exact sequence. TP is an epimorphism, and we know that we can actually build a short exact sequence by considering its kernel. But the kernel here, the kernel of the differential of P, it's exactly the tangent space to the fiber. And since the fibers are linear, indeed, the kernel for every point is going to be, for every point in M, is going to be the fiber at M. So the kernel is just the vector bundle E. So we have this short exact sequence, right? Because obviously this is an inclusion, and so it is injective. It's a monomorphism. Okay, what we have is that this sequence splits. We have to build here a map H, a morphism of vector bundles, such that the composition of H and dP is the identity of the tangent space. But what we have is that C, we can consider the zero section, which is an embedding from M to E, right? And we can consider its differential, which is a map from the tangent space of M to the tangent space of E, right? It's indeed, again, and indeed we have this. It's indeed, again, a morphism of vector bundles over the identity map. And now we just define H as DDC. What we have is that the composition of DDP and H is D of C composed with DP. This is the differential of the composition, right? But the composition, because of the chain rule, the composition of the zero section and P is just the identity map. So we got here the differential of the identity map, which is the identity map of the tangent space. And so we get that this sequence splits. And as a consequence, we see that the tangent space of E at M is isomorphic to the direct sum of the tangent space of M and the vector bundle E. Indeed, we can see that the situation that was described for the previous example is completely general. If we have a short exact sequence of CR vector bundles and R is between 0 and infinity, such an exact sequence is always split. And how can we prove this? We're not going to give the details, but if we have here a monomorphism of vector bundles covering the identity, what we need is finding a left inverse, okay? We need to find H such that the composition of F and J and H, sorry, is the identity of psi. And this is very easy to do locally. It is essentially linear algebra. And then we can paste these local left inverses by using a partitions of unity argument. In this lecture, we introduce exact sequences, and in particular short exact sequences, and we studied their elementary properties. In the next lecture, we are going to consider a different topic. Indeed, given a CR vector bundle, we are going to give a structure of inner product space to the fibers of the vector bundle that has a natural CR structure. Thank you for your attention.